Let's take a quick look at how environmental variables affect health. I think it's fairly obvious, but nonetheless. Here it is example of health outcomes due to variability in rainfall, emphasizing how the relation can be complex and depend on the environmental setting. So these are the references here. Health outcome is cholera linked with precipitation. Rain increases risk in dry areas and decreases it in estuarine regions. So you have to know what is the agent that is carrying this environmental bacterium Vibrio cholerae and how it gets consumed by people and what are the indicators. So rain, water, is always something that breeds the host that carries Vibrio cholerae on a hard shell like chitin, which is on copepods. Similar mucus exists in our stomach, so when you consume water with high enough concentration of Vibrio cholerae, it begins to explode in your stomach, and the body thinks it's an external enemy, so it begins to get rid of it by diarrhea and so on. Typically, it's body's overreaction that makes us sick, like in COVID, for example. Rift Valley fever, rain increases risk, which suggests that extreme rain separated by a dry period may trigger outbreaks. So you have to know the evolution of the environmental conditions that favor Rift Valley fever. Malaria, rainfall provides breeding sites for vectors. However, drought can lead to breeding sites as rivers dry. So rivers can leave shallow ponds where mosquitoes can breed as opposed to the flowing full river where they cannot. Dengue, rainfall can provide breeding sites, but low rainfall may increase urban storage of water, so people begin to put water in tanks, leave it out, and water that can become a breeding ground for mosquitoes, and then dengue can explode. So it's not just enough to know the relation between mosquitoes and dengue, but you need to know the habitat conditions on which mosquitoes thrive and how those conditions are related to temperature, rainfall. Extreme events, for example, can wipe out mosquito population and reduce incidences of dengue as opposed to steady rain and so on and so forth. Vegetation can help breeding of mosquitoes, etc. Okay, complicated relations, but typically what people do is to look for these kind of environmental variables to causative agent relation. I just picked one here. For example, you can take clam raiser, which people go around looking for in Seattle area during certain seasons, and there is empirical evidence of when they may be infected by things like Alexandrium. And domoic acid that's being looked at here is a neurotoxin which gives you temporary amnesia. It's produced by Pseudonychia, which is a diatom, which is a harmful algal bloom because it produces this domoic acid, which is consumed by shellfish. And when the birds eat the shellfish, or the mammals in the water, marine mammals eat it, they can die, they can have all kinds of issues. If you consume domoic acid, you will have amnesia and other neurological effects, and it can kill as well. In fact, the movie The Birds by Hitchcock was motivated by birds attacking people, I think in Santa Barbara in the 1960s, which was related to a domoic acid Pseudonychia outbreak. Happens regularly during El Niños, for example. So we're looking here at the Pacific Decadal Oscillation Index and the Oceanic Nino Index. So you can see El Niños and La Niñas, but you can also see the low frequency variability, which corresponds to the Pacific Decadal Oscillation. Associated with them are these temperature anomalies in the region that's being looked at in the Northwest Pacific, called the blob. Then you look for copepod species richness anomaly, which depends on these marine habitat conditions, and then you look for maximum monthly domoic acid in parts per million, and you look for relations, and then you can make forecasts of oceanic Nino indices and associated teleconnections to the blob region, let's say, and then you can estimate probabilities of domoic acid outbreaks. So very easily one can provide spring transition dates are shown here, for example. One can provide early warnings so that people can be careful about what they consume and not eat raw marine products like clams or fish and so on, and no regret decisions can be very easy. But statistical relations are fixed in time. They can be updated, but they tend to remain they depend on historical relations, with temperature changing constantly, precipitation patterns, intensity, duration, frequencies changing. You need to update the relations constantly. So the idea is to use dynamical relations whenever possible. So developing those here, schematic of the potential sources of uncertainty when using weather sensitive disease model to simulate observed health outcomes. So this is more sophisticated, but uncertainties can be will have to be dealt with as well in terms of using mechanistic relations. Okay, so boundary condition uncertainty, climate, environment, land use, socioeconomic, so data errors and spatial representativeness errors come in. Let's say we're worrying about malaria, then you have inputs which are affected by initial condition uncertainty, like epidemiological data, entomological data for mosquitoes that carry it, and hydrological data that affect mosquito habitats, and validation uncertainty. Then it has to go to decision processes. Decisions depend on individuals and agencies. Model process uncertainty, structural and parametric dependencies, and so on. So implementing models for health is not very straightforward, but this is showing some skill here, points where forecast skill is significant for temperature, rainfall, and an analog of malaria cases at lead times of 1 to 4 months over Africa, using reanalysis derived data for evaluation for the detailed okay, so I cut out some points there, but nonetheless you can see that relevant environmental variables have predictive skill in the Sahel region, which is and of course Congo and other parts of Africa, East Africa, Madagascar, and so on, depending on the season. So you can see here July, oops, I hate that, July, August, September, October, November, and December, so rainy seasons. So malaria has had some success in predictions, but data is always a problem. For example, here from month 2 onwards, only malaria is successfully predicted due to the lag between rains and malaria. So if you have rainfall skill for the first month only, and second month it doesn't have much skill, you can still get malaria skill that's good at 2 months, 3 months, because there is a lag between when it rains, when the mosquito population grows, and when they begin to transmit malaria and of course the parasite itself. So one has to be aware of how predictability depends on the relation. Okay, let me stop this here and then go to dengue in the next podcast. We'll just look at some case studies based on the experience of the authors. Obviously, we are just touching on them to focus on predictions and predictability, and we will touch a little at the end of the chapter on what are some of the challenges. As I mentioned, data is always an incredible challenge, not only for environmental variables, but much more importantly for health variables and behavioral patterns of humans, that is very regional and local, and then people movement. When you have infectious diseases, people movements matter a lot. Okay, but nonetheless you do the best you can to connect predictable environmental signatures to health outcomes and drive decisions that can reduce morbidity and mortality. That's ultimately the goal, and many agencies get involved, and this process is getting better with Ready, Set, Go, as we will see in the coming podcasts.